This is FE Peer Review. The date is the 21st of April, 2021. Why maths? Or as we Americans say it, why math? Well, this may turn out to be the first in what I think might become a three-part series, 3 episodes, you might say, on the subject of diagrams and mathematics and the use of trigonometry in this case. This grew out of a discussion I had with a certain Fred Campbell, who left a message on Baldy Cat's video. I believe he had this diagram in mind in his message. I responded. We have had some back and forth. Other people have talked with him. Our conversation has spilled over to one of my videos. And Fred has been an interesting person to talk to. He's been very polite and thought-provoking. He clearly sees things differently than I do. And I'm not always as patient as I should be, but he's been very patient with me. And he has stimulated me to explore these ideas. So the thing I'm seeing in some of Fred's words here are that he seems to have either a difficulty or a distrust or a concern about the way that this diagram that Baldy Cat's used as the basis for his trig was not drawn to scale, and is neither perspective. As orthographically, it's not drawn to scale, and it's not in perspective. And I may have misunderstood Fred Caldwell here, but I definitely came away with the impression that he seems to think that orthographic views need to contain perspective. And like I said, I may have misunderstood his words. Part of the problem we've been having in our discussion is that kind of thing. But here's really what caught my attention in one of the things that Fred said and what got me really going. He says, one thing I've noticed about side views, like I identified in the video, is that they do not take into account a viewer's perspective. Absolutely no perspective proportions for how large the mountain would appear to be at 83 kilometers away is identified in the illustration Katz gave. Absolutely no perspective proportions for how large the mountain would appear to be. When you're using trigonometry and you're working from actual distances, not apparent distances, not angular sizes, but actual sizes. And this is where I thought, okay, this needs to be addressed. So for this first of 3 videos, what I've done is, at the suggestion of Fred, he had indicated that he had done some sketches on paper to scale. I think he was using a 11 by 17 paper, and that's equivalent to a A3 paper for my European friends. I thought, okay, if we're going to do that kind of an observation and chart it to scale on paper, can you really get useful information out of that kind of a drawing? So I decided, and I told Fred I'd do this, to try to do one, and I will show you the pictures of what I came up with. This is the temporary workspace I've got set up in the loft of my house where I'm doing a bunch of remodeling work, and I've set up a little temporary work table in there. And so what I did was I took a strip of it. It's a piece of old kitchen countertop, and I sanded it down and put a couple of coats of white paint on it, got it as smooth as I could to make a nice long work surface. And in the back of it, you see here a 2-meter long level, which has got a very nice straight edge on it, which I checked, and I'll show how I checked it. For a start, I wanted to point out that when I place the level on my work table, there is a small sag of about 5 millimeters in the middle of the table. That would be in the middle here. Having been set up on these sawhorses for a number of months, the tabletop has sagged a little bit. Now, I raised that point because this is part of the problem. This is part of why we use math, because there are so many small factors where errors can accumulate when you're trying to use graphic techniques to make calculations that simply aren't there when you're working with the pure math. For example, is the little bit of sag that's in my work surface going to cause the line I'm about to draw on it to not be a straight line? It could, and I have to make sure to try to avoid that, and it may be impossible to avoid the problem altogether, even with my best efforts. So there's my level, straight edge, and I've laid it down on the table and I've drawn a line. A little hard to see the line, but you can see it, perhaps you can see it along here. And now what I'm going to do is to demonstrate that I've got a straight line and a straight edge, I'm going to take my straight edge and flip it over. There, flipped the other way. And in doing that, I can line it up with the line I had previously drawn. If my straight edge itself were not straight, this would become apparent with this little test, because the straight edge would, the error in the straight edge would be doubled and easier to see. So this is a little technique that has to do with, you might say, calibrating your instruments. Now, I meant the length of my table is about 74 inches. You see inches on the top of the scale and millimeters on the bottom. I'm going to stick with inches throughout because the distances we're going to be looking at were measured in feet and miles. So just to be consistent, I'm going to stick with inches in my drawing. So my work table is about 74 inches long, and I need to do a drawing on this surface that's to scale. So let me skip over to just a little table that I put together in Excel. Now the view that I'm drafting out here is not the exact view that was in Kat's video. This was another view of Blackpool Tower with the mountains in the distance, and the observation point was called Thirst-Aston Hill. This was a view that was circulating about 8 months back. I did a video on it, Ruhif did a video on it, I think Blue Marble Science might have done one. It was in response to some stuff that Exploring the Plane put up. I'm going to use that image and that video as the reference here. So we had an observation point at Thirst-Aston Hill, which had an elevation of 298 feet. And then we had the Blackpool Tower. We have an elevation of 420 feet and a distance, which I've got in both miles and feet. Red Screes Mountain, an elevation and a distance in both miles and feet. And then I used Walter Bislin's curve calculator to get a horizon drop at Red Screes and at Blackpool relative to the observation point at Thirst-Aston Hill. I needed to develop a scale that I could use to draw this on my tabletop. Well, I found that a scale of 1 inch equals 6,000 feet pretty much maximized the use of the tabletop. It got me to within a couple of inches of each end. So on the basis of that scale of 1 inch equals 6,000 feet, I took the elevation of Thirst-Aston Hill and I converted it to inches. And it comes out to 0.049 inches, which in terms of 30 seconds of an inch is 1.59 30 seconds of an inch. So what I did was I took that number, and that's what I used to scale on my tabletop. I did the same for Blackpool Tower, the elevation, and also its distance from the observation point, and Red Screes. So what you're seeing in this picture here is I'm down at the Red Screes end, which is on the right side of my table, and I have the black line represents the line, a flat line between a flat surface, not a curve based on the radius of the Earth, but a straight line. The height I've measured here is 2, 4, 6, a little bit more than 6/16 of an inch, which is what I got for the height of Red Screes using my 13/30 seconds or 6.5/16. So that's Red Screes drawn to scale from mean sea level to the top of the mountain. That's the Blackpool Tower. The black line is mean sea level. The little parallel pen line is the height of Blackpool Tower, and these are 1/16 of an inch marks. And there's Thirst-Aston Hill, a little less than a 1/16 of an inch. And to give you a sense of the scale of all of this, I've placed a pencil back here at Thirst-Aston Hill, a pen at Blackpool Tower, and another pen at Red Screes. Red Screes, which was by far the tallest object, you can see the two lines. There's Red Screes. You can see from the scale of the size of the pen the dimensions we're talking about. That little tip of that pen there is bigger than the mountain. And there it is relative. So in working to scale graphically, to do an observation like the Blackpool Tower, Red Screes Mountain, you've got to go over along this line a good 70 inches, and you're going up 3/16, 3/8 of an inch, 6/16 of an inch. Now that's the triangle that we're talking about, that if Katz had done his triangle to scale, it would have looked like that, which I think you can say is impractical for the demonstration Katz was doing. And really, in my opinion, not necessary. Okay, so there's Red Screes. Moving on. Now what I've done is we're at the Blackpool Tower location. I have marked with the dashed blue line below the black pencil line the horizon drop as I got it from Walter Bislin's Earth Curve calculator. So the distance, the amount of horizon drop from my observation point to Blackpool Tower is from the black line to the dashed blue line. And then I've drawn the height of Blackpool Tower relative to the horizon drop, relative to the globe drop. Excuse me, I should say globe drop is what I'm drawing here. I've drawn that with another little tick mark. So the upper tick mark is the height of Blackpool Tower relative to a flat surface. The lower tick mark is relative to a curve of the Earth's radius. And then I've done the same at the Red Screes location. The black line is the flat surface, the dashed line is the globe surface. We have Red Screes mountain based on the globe or based on a flat surface. And now the pièce de résistance. We have a green line that connects the top of Red Screes to my observation point way far away on the left, based on the flat geometry. And then we have a pink line connecting Red Screes to my observation point based on the globe geometry. And back here at Thirst Aston Hill where I'm standing, you can see the pink and the green lines come together and meet at my observation point. And at Blackpool Tower, we see that the green line, which represents a line of sight, a straight line of sight, none of this is taking into account any form of refraction, a straight line of sight from the top of Red Screes to my observation point, passes well above the top of Blackpool Tower. Whereas with the pink, with the globe geometry, the pink line represents the same straight line view from Red Screes to my observation point, and it passes pretty nearly through the base of Blackpool Tower. I put the scale back next to the drawing just for reference. Each tick on the scale here is a 1/16 of an inch. And finally, this is where we run into a problem. Trying to determine the angles and the difference in angles between the elevations that we're seeing, the angular dimensions of these objects relative to the observation point at Thirst Aston Hill. I have placed a protractor on here, and as you can see, we are unable, the lines are so close together that we are unable to read an accurate angular dimension off of this protractor. We're within the 1 degree mark. So is it 0.5? Is it 0.47? Is it 0.2? Is it 0.6? Your guess is as good as mine. Basically, as a graphic approach, even though I used a 6-foot long work surface and was meticulous in trying to do my setup with sharp pencils and straight lines, I can't get the kind of information I need from this graphic visual approach. Graphically, I actually got a little more out of this than I expected, and I'll show you what I was surprised at that did work. However, I do just want to reiterate, I could not get a measurable angular dimension using this approach, which was what the trigonometry does so well. There was, at being well under just 1 degree, there was no way that I could graphically read that off of my protractor. Even if I'd had a much larger protractor, I would never have been able to do anything more than estimate, well, about a half a degree. And to get the difference, I wouldn't have been able to get the difference at all. So what did surprise me was that, we'll look at this compared to what Walter Bislin's calculator shows. The pink line, that's the red screes factoring in the globe surface, the radius of the Earth, with zero refraction. There's no refraction in any of this. It shows the top of red screes at pretty near the bottom of Blackpool Tower. And if we look at the curve calculator, I've put red screes, as the larger objects in back, and Blackpool Tower, and I've set refraction to 0. And as you can see, if there were no refraction effects at all, red screes would be considerably farther down the tower than it appeared in the photo. I will bring the photo up in a minute. With refraction, red screes appears near the top of the tower, which is almost exactly where it shows up in the photo, and that's standard refraction. That's not any kind of unusual refraction level. So my diagram was pretty good. It probably underestimated it, probably put it a little too low, but it was pretty good at catching that. However, as I said before, it did not yield results which I could use as measurements. For reference, this was the photo I was mentioning. This was the one that was going around about 8 months ago, and we see red screes in the back here, and the top of it is it aligns pretty much with the observation deck of the tower, so near the top of the tower. When you have zero refraction, it puts the base much lower. I have one more point to address here, and it was to do with the comment I left, which said, for argument's sake, supposing the Earth is curved and assuming no atmospheric refraction, since we're treating this as strictly a geometric exercise based on measured distances, according to Walter Bisland's Earth calculator, 2112 feet of red screes' total height of 2446 would be hidden, leaving only 334 feet visible. What is the difference in angular size between an object measuring 334 feet in height compared to an object measuring 2,446 feet when seen from 77.6 miles away? Can this difference be reliably measured with a carefully hand-drawn diagram using drafting tools? I will include the answers in my follow-up video. I hope you will too. I had asked Fred to do this himself. I hope you will too. Well, Fred responded, quote, what is the difference? He responded by quoting my bit, and then he said, anxiously await your response to that question. Now, Fred, I happen to know, is busy with some other tasks, life tasks that can't be avoided, and he's not free to just go off at his spur of the moment and do this, so I'm patient to wait for Fred. However, I do hope that when Fred does have the time to respond, he also does make the same, answer the same question I did and provides me with the method by which he did it. So I will now show you how I went about and got the answer to those questions. We see three triangles on this sheet here. The top triangle, this one up here, is drawn to scale with the observer at the left and red screes at the right. Again, no curvature, Earth curve. This is just a triangle, a straight line across the base. And I'll zoom in, and what we see here is to scale. The longer line represents the actual height of red screes, and the shorter line, the 334 feet, that would be seen, it would not be hidden by Earth curvature, to scale. Now, as a diagram for illustrating trigonometric calculation, I find that not helpful. So if I go down here, this one is a copy of this one in which I have altered the vertical scale. So strictly speaking, the proportions of the two vertical legs it's proportional. However, it doesn't need to be to serve as a diagram to illustrate a mathematical equation, because again, these are still rather awkward, tight little areas to work in. The third triangle at the bottom here is not to scale. The two heights are not to scale according to the dimensions given. None of that matches the base, but it provides an easy place for me to indicate which angles I'm looking at and which heights I'm looking at and what my what all this refers to. So we have the base B, we have A1, that's the total height, we have A2, that's the lower height, we have the angle associated with A1 and the angle associated with A2. As a diagram, it's 100% clear what I'm referring to. There is no need for the diagram to be to scale. That's my main point here. No need for the diagram to be to scale when it's simply to illustrate the math, because the real work is being done in the math. So here we are. I've made this little table in Excel. Difference in angular size between an object measuring 334 feet and 2,446 feet when seen from 77.6 miles away. A1, 2,446 feet. A2, 334 feet. B, that's the length of my base. That's the distance between my observation point and red screes, 409,728 feet. I take the height A divided by the base, and I get a fraction. I take the second height divided by the base, and I get a fraction. I use the arctangent formula to get and convert it to degrees to get an answer in degrees for A1. A1 is 0.342 degrees. A2 is 0.0467 degrees. You may recall when I had the protractor out on my drafting table, on my work table there, that we could see that the two lines were somewhere within the 1 degree mark, but we could really not tell where. We would never be able to read off of that protractor that one line is at 0.342 degrees and the other at 0.0467 degrees. Simply impossible to get that kind of fine level data off of that nice big 6-foot long drafting surface I created, on which I carefully drew. So the difference, to answer the question I had posed, is 0.295 degrees. So the difference in angular dimension between those two heights is just under 0.3 degrees. That's how little it is in angular dimension, and yet it is very important to be able to measure it, because in measuring it we learn a whole lot about the world around us. But we can only do that measurement with math. We can't do it with pencils and drafting equipment. Conceivably possible, I shouldn't say can't. It would be extremely difficult, time-consuming, and require a lot of very precise instruments which are very prone to error. I mean, the thickness of the pencil line is a problem. So yeah, maybe not impossible, but trigonometry works. That's what it comes down to. Trigonometry works. I'm going to do 2 more videos in this series. This is the first one, and the second one I'm going to do is there's a parking lot, a parking garage with a shade structure that's got a whole straight row of columns, and I can measure the distance between the columns. I can use the trigonometry to determine what the angular size is, the angular dimensions are of each of those columns based on an observation point. I can then take a photograph from that same observation point and see if the results of the photo match what the trigonometry tells me. That's a way of confirming that the trigonometry is working. The third video I'm going to do is platform habitat, the notorious so-called black swan. We've all seen the highly refracted photograph that allows us to see nearly to the base of the legs of the platform, and we've all seen the regular photograph where the base is pretty thoroughly concealed. I'm going to try to get my hands on, or estimate as best I can, the actual dimensions of platform habitat. And I'm going to measure how much angular change that high level of atmospheric refraction causes a beam of light that's coming from the platform to an observer on the beach, and try to determine just how much of an angular change it takes to change the view as we saw it between those two photos. That kind of fits in with a similar geometric problem. So those are the two more videos I'll be doing in this series. Anyway, I hope you enjoyed this one. It's kind of pedantic. I think it's a message that I needed to put out there, and I think that this might be useful to Fred Caldwell and hopefully other people. If you should find yourself talking with somebody who's distrustful of the math involved and wants things to be drawn out, I hope that this video will be useful in that discussion. You all have a great day. I hope you liked it. Click the like button, share it, all of that. Look forward to hearing from you. Please leave comments. I love comments. That's my favorite thing. Bye-bye.